Good afternoon. Today, Team 11 is going to present our cumene production process. I'm Amanda.
I'm Chris.
I'm Jessica.
I'm Jordan.
I'm Shike.
This presentation will cover the product, process, and economics of the cumene production plant. First, Shike will be covering the background information of the cumene problem statement.
In the U.S. Gulf Coast, the cumene production plant produces 407 million pounds per year of cumene using a new zeolite catalyst, which leads to higher benzene to cumene selectivity and higher cumene product purity. There are two different reactions in the plant that utilize benzene in order to produce cumene. So the first one utilizes benzene and propylene in the alkylation reactor to produce cumene, and that's where we get most of our cumene production. The second one utilizes benzene and DIPB in the transalkylation reactor to produce cumene. Now I'm going to hand over to Chris to talk about our PFDs.
Okay, so here you can see our overall process flow diagram for the process that we designed. There are several different unique characteristics of this process design. Specifically, we utilize a benzene recycle stream that attempts to conserve as much benzene as possible in order to cut down on our raw material costs. This process also utilizes a purge in order to cut out any unwanted impurities from building up in the streams that are very difficult to remove elsewhere. Here we see our initial benzene feeding into the first benzene separation unit. This is used to remove N-hexane from the benzene feed in order to meet reactor feed specifications. Interestingly enough, this waste stream is high enough in purity of benzene to sell at a 95% purity. So this waste stream is sent to a storage tank in the OBL where it is sold. Here we see the benzene feed that is sent through several separation units to be purified before entering the reactors. Here we see the initial benzene feed as well as the recycle stream exiting the reactors sent into the first benzene purification unit. This separates the benzene and other lighter chemicals from the products of the reactors, mainly cumene, DIPB, and heavies, which are sent down here. First, the benzene is sent into this initial benzene recovery unit, which is used to separate toluene, which is another reactor specification. This toluene waste stream is high enough in energy content above 10,000 BTU per pound, so it is sent to the liquid fuel system in order to generate fuel credits for our process. This benzene stream is then fed into a flash drum to remove any gaseous impurities that are building up in our process, mainly hydrogen and propane. Again, this vapor waste is high enough in energy content to be used for our vapor fuel system to create fuel for our process. This benzene stream is then split and sent partially into the alkylation reactors and partially into the transalkylation reactors. Here we see the benzene stream that enters each of our reactors. So as you can see here, part of that benzene recycle stream meets with the propylene feed, and this enters the alkylation reactors. We have 5 sets of 2 reactors in series, giving us 10 total alkylation reactors, with 2 reactors kept as spares and that are also used for catalyst regeneration. Here, we have the other portion of our benzene recycle stream that meets with our DIPB recycle stream and enters our transalkylation reactor here. The outputs of both of these reactors meet here and then enter our purge. We have a purge ratio of about 10%, and this is used to remove any impurities that are difficult to remove elsewhere in the separation units, mainly cyclohexane, whose separation is very difficult. Here we see the bottoms from the benzene recycle stream purification that were discussed earlier. This is first sent into the initial cumene recovery unit here, which separates cumene from DIPB and heavies. Now, this cumene product is then sent to a second cumene recovery unit, which purifies the cumene to our specified final purity of 99.9%. This cumene product is then sent to the OBL for product storage. Again, the waste product from this separation is high enough in energy content to be used for the liquid fuel system. Finally, here we have our DIPB recycle unit. This separates DIPB from the heavies, which are unable to be sent into the transalkylation reactor. The heavies waste from this process is unable to be used in any sort of fuel system, so it is sent to the OBL storage tank. And the purified DIPB stream is sent to the transalkylation reactor. Now I'm going to pass it off to Amanda, who's going to discuss our process specifications.
Thank you, Chris. Now I'll be talking about our product specifications. In this pie chart, you can see that we are meeting 13 hard specifications, we're not meeting 8 hard specifications, and we are not meeting 5 soft specifications. These specifications are on our unit temperatures, stream concentrations, and the final product that we were given in the problem statement in order to encourage best practices for the design engineers. Team 11's cumene production plant is currently meeting 62% of the hard specifications. These hard specifications are required, especially the capacity and purity of the cumene product. So again, this pie chart reflects that there are additional soft specifications that I will be discussing. From this table of specs being met, the cumene production plant successfully reaches cumene capacity at 407 million pounds per year at 99.99% purity. Throughout the process, the distillation columns remain under the maximum temperature as well. The group successfully meets 10 specifications regarding the composition of the streams entering the alkylation reactors and the transalkylation reactor, as well as the specifications regarding the composition of the cumene product effluent. While we were successfully able to meet the capacity and purity for the plant, some soft specifications were not met, which are listed in this table. The current design has a high percentage of benzene going to waste and poor benzene utilization in the reactor, which is only 28%. This attributes to high feed volumes of benzene with high feed costs. Also, there is poor propylene utilization. It's only at 41%. This poor utilization of reactants can be attributed to the need to adjust pre-exponential factors in the kinetics equations, which will be discussed later. However, cumene and DIPB recoveries are close to the desired specifications at 81% and 69% respectively. This highlights the efficient functionality of the process design and how our team was able to successfully recover our desired products of DIPB and cumene. As I mentioned previously, our design could be improved in the alkylation reactor with its kinetics. This would ultimately improve our selectivity to cumene and improve the conversions in the reactor. Currently, the reactor is experiencing 100% propylene conversion. This is because the K values in the reactions that form ethylbenzene and butylbenzene are much smaller than they should be in order to meet the desired selectivity specifications. There is a less than desirable propylene selectivity to cumene and a higher than desirable propylene selectivity to cyclohexane. This causes a surge of cyclohexane in the process. In summary, the kinetic calculations can be adjusted in order to improve the overall selectivity to cumene. Now, Jess is going to discuss our economic evaluation.
So first, I want to talk a little bit about our annual cash flow, and it ends up being around negative $178.79 million per year. And if you look at the pie chart below, it depicts all the ongoing costs that go into calculating this cash flow. Evidently, the raw material cost overpowers all of the other ongoing costs for this cash flow. These other costs include the utilities, the fixed costs, and the SG&A costs. Next, our total capital for the plant comes to around $166.7 million, and there are three main contributors to this cost. First, we have the TCC, which is known as the total contractor cost. This includes the IBL capital at around $76 million and the OBL capital at around $23 million. The OBL capital was found by calculating the upgrades with an original bid. With these two added together to get the TCC, next there is the CPE, known as the current point estimate. This includes four different costs. These are team costs, miscellaneous costs, startup costs, and catalyst costs. All of these added together create the CPE. Finally, we have the contingency on the project, which was 20%. In order to find this, we took the escalation, which we calculated to be 14.5 million, added it to the CPE, and then multiplied by 20. So all three of these values added together will create the total plant cost that we got. Next, I want to talk a little bit about the revenue that we get from our plant. There are three different streams of revenue for this plant. One is the cumene product. Next is the benzene product that we are able to sell coming out of T101 at a 95% purity. And finally, we have the liquid and vapor fuel streams that we can generate energy from. And all of these added together give us a plant revenue of $233.3 million per year. Cumene obviously generates most of the revenue, coming in at around $170 million per year. Then we have the waste fuel, which is around $40 million per year. And finally, the benzene, which is around $25 million per year. And it's interesting to note that the annual plant revenue at 233 is about $100 million below that of how much our raw materials cost, which is one of the main contributors to why our cash flow is around negative $178 million per year. Next, I want to talk a little bit about the lifespan of the plant and how profits will be handled. So over the 15-year lifespan, selling at our current cumene price of 42 cents per pound, there will be no profit. And this shows that the NPV12 is around negative 718 million, and the cumulative cash flow is around negative $2 billion. So if we look at our required net back to achieve an ATROR of 15%, we'd have to sell our cumene at 85.89 cents per pound. This would generate a cumulative cash flow of around $195 million and an NPV12 of around $17.5 million. This means that we would have to sell cumene at over double its original price. And if you look at the next slide, you will notice that if we sell at 85.89 cents per pound, we would start making a profit after the year 2030. Next, Jordan will speak about conclusions and recommendations on the project.
After analyzing the economics on our base case, we concluded we should not move forward with the construction of our plant. We meet cumene purity at 99.9% and cumene capacity at roughly 48,000 pounds per hour. However, our poor utilization of benzene and the cumene selectivity in the reactor prevents our current base case from being profitable. Our group calculated several alternate and sensitivity analyses after finishing our economics on the base case scenario in order to determine if the plant is ever profitable. As stated earlier, we calculated a cumene price of 85.89 cents per pound to reach a required netback of 15%. Looking at the project's cumulative present worth over 15 years, we can see that the plant becomes profitable after the year 2030. However, it is not common that the cumene price will nearly double in today's market. This indicates that this sensitivity analysis is not realistic and will not be successful. Another sensitivity analysis was completed in which we receive a free benzene feed from another process in the plant. Our feed costs account for most of the costs in the plant. Therefore, obtaining a free benzene feed will drastically reduce this cost, feed cost. And as you can see from the cumulative present worth graph on the right, the plant becomes profitable after year 2025 in comparison to the base case that never becomes profitable. Therefore, this is a viable option our team could pursue in order to start construction of the plant and make the plant profitable. Thank you for watching, and we hope you enjoyed our presentation.